Your spring break. I hope that you guys had an excellent spring break. So Mr. Carizales will be covering Mr. Isasi's session today. So if you're in 1324, they'll provide the link for you. And so today we're going to start with chapter 3. And chapter 3 is a really exciting chapter because it's applications that we see almost every day, everywhere. So at any time, if for some reason you can't hear me, just let me know. So, and I apologize in advance as well. You might hear some Cocomelon music in the background, but hopefully it's not going to be too loud. So what is an exponential function? Basically, an exponential function is going to look like this, where we have f of x is equal to a to the x power. So here, the a is actually going to be a number. So in the past, we were using, for example, x squared. So the base was an actual variable, but now the variable is going to be an exponent. So for exponential functions, the domain is a set of all real numbers and the range is a set of all positive real numbers. So we'll get a glimpse at how it works. So here's just a problem that to show you how exponential functions grow. So suppose you received a penny on the first day of class, and then 2 pennies on the second day of class, and 4 pennies on the third day, and so on. Or you could get $1 million. Which one would you choose? So let's see how what we would have after a month. So if we chose to get a penny on the first day, 2 pennies on the second day, and then 4, 8, and so on, how many pennies would we have on the 31st day of the month? And so we can see a little pattern here on the right. So the number 2 here can be written as 2 to the first. The 4 can be written as 2 squared, and so on. So on the 31st day of the month, we would have 2 to the 30th power. And if we put that in our calculator, this number is going to be right here. But if we move the decimal points to the left, then we could earn $10 million. And so choosing the pennies was a better option, but you can see how fast this grows. So when we had the COVID hit, it was at the beginning, it was growing exponentially really quick. And so if you were to graph that, you could see it's kind of growing exponentially, and then it kind of flat out towards the end of the pandemic. Okay, so let's see what this graph looks like. So if we were to graph it, then the graph is going to be a little curve like this. And so here it's important to see that a has to be greater than 1. The domain is negative infinity to positive infinity. The range is 0 to infinity. And the y-intercept is 0, 1. Okay, so this graph is increasing, and then it also has a horizontal asymptote at y equals 0. Okay, so our graph is continuous. But we could also have a function that is decreasing, and that's going to occur whenever a is between 0 and 1. So basically, if a is a fraction, or if a is greater than 1, your exponent would be negative. Okay, so here our domain is negative infinity to positive infinity. The range, the y-intercept, those all stay the same, except the function is now decreasing. Okay. So let's graph 3 to the x. So anytime we start a new section, we have to go ahead and when we start a new section, we want to know what these graphs look like. So we can construct a table of values. And so on the left side here, I have a table of values. So if I input a negative 2, I can use the exponent property. So with this 3 to the negative 2, I can write it as 1 divided by 3 squared, which would be 1/9. And if I input negative 1, then we get 3 to the negative 1, which would be a third. And then anything to the 0 power is going to be equal to 1. And then 3 to the 1 would be 3. So these are my points. If I plot my points, then I can see my points here. And if I sketch the graph, then this is going to be my graph. So notice that my base was a greater than 1, and so that is why the graph is increasing. Okay. So let's talk about a horizontal line test. In the first chapter, we learned about vertical line test, and the vertical line test was used to determine if an equation is going to be a function. In this section, actually, and also probably in the first chapter, we also saw the horizontal line test, and that was used to determine if a function was one-to-one or if it had an inverse. And so for this section, exponential functions are functions and they pass the horizontal line test. And so therefore they're going to have an inverse and they're one-to-one. So the inverse of the exponential function is a logarithm, which we'll talk about in a few minutes. But I want to focus on this one-to-one property. So the one-to-one property tells us that for a greater than 0 and a does not equal to 1, if we have an equation where the base is the same, then we can set the exponents equal to each other. And so this property will help us to solve equations that look like this. So if I had 10 raised to the power of 2 minus 4x equals to 10 raised to the power of 6x minus 1, since the base is 10 on both sides of the equation, then I can set the exponents equal to each other. So we're going to apply the one-to-one property. So I have 2 minus 4x is equal to 6x minus 1. So our next step would be to solve for x. So I'm going to go ahead and subtract 6x on both sides. I'm going to subtract 2 on both sides. And so that gives me negative 4x minus 6x is negative 10x. And negative 1 plus negative 2 is negative 3. Divide by negative 10. So we get 3 divided by 10. So 3/10. Okay. So let's try a couple of more. So here it says solve the given equation. Can we use the one-to-one property? So the criteria in order to use the one-to-one property is that they have the same base. So here I have a 4 and this one has a 64. So they don't have the same base, but the next question you want to ask yourself is, can we make one of these bases to be the same as the other? So this 64, I could change it so that we can rewrite it to have the same base. So notice that 4 cubed is the same as 64. So now my base on each side of the equation or the equal sign is 4. So now I can apply the one-to-one property. So I'm going to have x plus 1 is my exponent on the left side, and then 3 is my exponent on the right side. Solve for x, so I subtract 1 on both sides, and I get x is equal to 2. Okay. So the one-to-one property is a nice property that can help us solve these type of equations. So again, remember that these equations, the big difference is that your variable is now an exponent. Okay. Let's try another one. So here we have 5x minus 3 is equal to 1 over 125. So as we can see on the left side, our base is 5, and on the right side, we have 1 over 125. So they do not look the same. However, we can try to make it the same. And so let me just use my pencil really quick. So this number here, I can actually write it as, 1 divided by 5 cubed. But if I want to bring the 5 cubed to the top, then by the property tells me that the sign would have to change. And so that's where I got the 5 to the negative 3. Okay, so now the bases are the same. So we can set the exponents equal to each other. So we get x minus 3 is equal to negative 3. If I add 3 on both sides, then I get x is equal to 0. Okay. I think I have another one. Okay, so in a little bit, we'll do a few more one-to-one properties. So now we have another one, another exponential function with base e. And so this number is a special number, kind of like pi, but it's its own, its number e is equal to 2.718, and it's going to go on forever. We call this the natural base number. And in your calculators, you will see this little E sign, and it's usually close to the log key. It's actually close to the natural log key. And the natural log key is close to your log key. Okay, so let's go ahead and move on. So since E is a number that is greater than 1, then the graph, if you were to graph it, it's just going to look like this, similar to the other one we had. Yep. So here I have e raised to x squared minus 3 is equal to e to the 2x. So the question is, do they have the same base? And so the base here is e, and the base here is e. So our next step is we can set up the exponents equal to each other. So we're going to have x squared minus 3 is equal to 2x. Notice that what's left here is an equation that is quadratic since we have a power of 2. So in order to solve something that is quadratic, we have to take everything to the same side. So we're going to go ahead and take this 2x to the left side. And let me go ahead and do that. So I get x squared minus 2x minus 3 is equal to 0. So since this is quadratic, then we have some options. We can factor, or we can use the quadratic formula. I always like to factor or try to factor to see if it's factorable. And in this case, it is. So we have x minus 3 times x plus 1 is equal to 0. We can set each factor equal to 0. So x minus 3 is equal to 0. X plus 1 is equal to 0. So we end up with x equals 3 and x equals negative 1. Is there any questions on this property here? So again, the main important thing is that your base has to be the same if you want to set the exponents equal to each other. If they're not the same, then we're going to have to do some other methods, which we'll see in a little bit. Okay. Another, all these problems, by the way, are from section 3.1. So another part of this section is compound interest. And so compound interest is used for credit cards, it's used for investments, and so on. And so the formula is given by a equals p parentheses 1 plus r divided by n raised to the power of nt. So a is how much money you're going to have in the future after your investment. P is how much you're starting with. And then r represents your rate in decimal form. And then n is how it's going to be compounded, the interest. And the choices for n is compounded monthly, compounded quarterly, compounded yearly, compounded daily, compounded semi-annually. And so I'll talk about those here in a second. And then t represents your time. Okay. So if it's compounded semi-annually, then n would be 2. If it's compounded quarterly, then n would be equal to 4. Monthly, you would use 12. 365 would be daily. In some textbooks, instead of 365, you might have 360. So the book will let you know. So some textbooks give you some holiday time in there. But for the most part, the textbook will let you know what to use for daily or for daily. All right, so let's try an example. Find the amount to which 1,500 will grow if deposited in a bank at 5.75% interest compounded quarterly for 5 years. So I always like to write down my variables. So for example, let me see if I can use this pen. I would write down A. Oh, I guess, let me try again. I'm on a different computer, so it's kind of, so I have A, I have P, I have R, I have N, and I have T. So these are all the variables in my formula. So for T, T is the time, so they give me 5 years, so I would use 5. They give me the rate of 5.75%, so I need to change that to a decimal, so that would be 0.0575. And then they give me a 1,500, so I have to decide, is that going to be my A or my P? So if we read this again, find the amount to which 1,500 will grow. So that means that 1,500 is what I start with. and I'm trying to see how much it's going to grow. Then the other clue words are compounded quarterly. So since it says quarterly, I would use a 4. So I always like to write down the variables and then see what is left over. So it looks like we're going to have to solve for A. And so let me just go to the next slide. Okay, so these are the numbers we just found. And if we plug them into the formula, then we're going to have 1500, 1 plus 0.0575 divided by 4 raised to the power of 4 times 5. So let me just see if, okay, I thought I had a different place. But let me give you some pointers when you're doing this on the computer. If you round in any part of this equation, then the computer is going to count it wrong. So what I like to tell my students is, if you on your calculator, if you know how to enter the entire thing, you would have to use parentheses around some of this stuff, then you can do that. But if you're not sure, because some calculators are picky on where you put parentheses, then take it one step at a time. So you can do 0.0575 divided by 4. Whatever number you get there, then just say plus 1. Whatever you see on your screen, you would write 1 point. And if it's 10 numbers that you see, I recommend that you write the 10 numbers. And actually, you could just say times 1500 and then raised to the power of 20. But nowhere in here you should round off until the very end. At the very end, then that's when you can round to 2 decimals, since we're talking about money. Okay, so let's go on to the next one. So here we have a couple just had a baby. How much should they invest now at 5.8% in order to have 35,000 for the child's education? Or maybe they want a quinceañera or something like that, right? And it says assume a 365 day per year. So you're gonna have to decide which formula do I want to use, right? So far you're gonna have 2 formulas. You have the compound interest or the continuous compounding. So if you see the word continuous compounding, then you use the different formula, which is A is equal to PERT. But if here it says compounded daily, so if it says compounded daily, compounded quarterly, compounded monthly, then you know to use this formula. Okay, and so here the 35,000 is what you want to have in the future, so we call that A. And then P is what we're going to try to figure out, how much do we need to invest right now. And then R is your rate, so they tell me 5.8%, so I'm going to write it as a decimal. And so in this here it should have been 0.058. And then we have our N, which is 365, and then our T, which is 18. Okay, so just to save us time, let me go ahead and instead of this number, I'll put 5.75. That way it's a little bit easier for that. Okay, so so I guess we corrected it on the next slide. All right, so we put in our information, and so we're gonna break it down step by step here. So first, we would divide 0.058 divided by 365, and notice that I get all of this number. So the question, or one of the mistakes I see done, is that students or anybody, whoever's doing this, will go ahead and say, well, I don't want to write everything, so I'm just gonna stop here and I'm gonna round. Since I have a 5, I'm gonna make that a 2, and I'm just gonna cut it short right there. And so if you do that, then you start to lose some pennies, right? So, and those pennies can add up at the end. So that's why we recommend that you just write everything you see on your calculator, and then you add 1. So we're gonna add the 1. So now we have this big number. And then 365 times 18 is 6,570. And so then my next step is to go ahead and put this in your calculator. And so that comes out to this big number, or this number here, 2.84, and so on. Again, if you round to 2.84, it's going to cause your answer to be wrong. Okay, so in math, it's going to count it wrong for you, but in life, it's going to steal away some pennies that eventually add up. So now we can divide. And so that's going to tell us that this couple should invest $12,322, okay, with 55 cents. Okay, so let's go on to the next part. Okay, so here are the two formulas that I was referring to. So whenever you're reading a word problem, if it says continuous compounding, then this is a formula you want to use. A still stands for your future value, P is your present value, R is your rate, and T is your time. But E is just going to be your natural number that is in the calculator. And for one of the mistakes that I see happen here too is that people like to write down, instead of using the key for your calculator, they say, oh, okay, well, E is 2.7 whatever. And so they just round the number for E. But you don't want to do that, because then it's going to count your answer wrong. So you actually want to hit the key for the natural log. Okay, not for the natural log, but for the E. Okay, so here we go. So those were all basic problems for 3.1. So you just wanted to, the highlights there are, do you know what the graph looks like? Can you graph an exponential function? And can you use the one-to-one property? And then applying those two application problems. So for 3.2, we're going to look at something called a logarithmic function. And the logarithmic function, as I mentioned earlier, is the inverse of an exponential function. And you'll see a picture of it a few slides from now, or I guess the next slide. So here you can see that you have your exponential function, which is y equals 2 to the x. And since it has an inverse and it passed that horizontal line test, it does have an inverse. And the inverse is the log function, which looks like this down here. So you can see that they're inverses of each other. Something I want to highlight here is that the domain of the logarithmic function, which is in blue here, is from 0 to infinity, where 0 is not included. Okay, and then your range is everything. So let's go to the next page. So we have a common log and a natural log. Okay, so we have, give me a quick, okay. So our common log is going to be written like this, where it has log x, but you don't see a little number here. Okay, the base is represented by this little number. Whenever it's missing, then you know that it's a common log of base 10. And this one is included in your calculators. So if you have a calculator and you see the word log, then it's assumed it is a log, but it has a base 10. If you see the word natural log or ln, then this can be written as log with base e. So in your calculator, you should see a key that says ln, and that means that it has a base of e. One of the mistakes I see happen is when you're inputting your answers in the computer, people will put an I instead of an L for the natural log. Okay, so this is an L for natural log. So let me go on. This log here has a base of 4. And so what we want to do in the next examples is we want to convert from logarithm to exponential, or from exponential to logarithm. And the reason that we want to be able to convert from one form to the other is because then we can solve for the equations. Okay, so let me go ahead and let me go back one slide really quick. And okay, I thought I had a different slide in here, but we don't. Okay, so let me go ahead and write something that is missing here. I must have deleted it when I updated the slides. Okay, so if you have a log with base b of, let's say, some number m is equal to n. Okay, so this is your log. So this in exponential form can be written as you start with the base. So this would be the base. I would write the b. And then the log is always equal to the exponent. So since this log is equal to n, that's going to make that my exponent. And then the other number, m, is going to be on the right side. Okay. So this is how we convert from one form to the other. And the keywords here is that I like to remember is that the log is always equal to the exponent. So that always tells me what my exponent is going to be. Okay. So let's try some examples. All right, so we have log 4 of 16 is equal to x, and we want to change this to exponential form. So my base is 4, so I write my 4. And then notice here, the log is always equal to the exponent. In this case, the log is equal to x, so that makes x my exponent, and then I have 16. Okay, so let's try some more. Here I have 125 is equal to 5 cubed. So in this example, what is my base? Is it 125 or is it 5? What would be my base? Anybody want to take a shot at it? So is it 125 or 5? So my base is going to be 5. And this equation is in exponential form. And so we want to write it as a log. Okay. So what I like to do, and I'm going to use my pencil again so you can see it step by step. Since I want to change this to a log, I'm going to write the word log. Then I ask myself, what is my base? So our base is 5. So I'm going to write the little number here. And then I'm going to put parentheses and equal sign. So now I know that the log is always equal to the exponent. So in this equation here, my exponent is 3. So that's going to be on the right side. And then my other number is what goes in here. Okay. And so log base 5 of 125 is equal to 3. And so let's go ahead and go to the next one. Okay, so that's what we had here. And let's try this one. So now I have log b of 27 equals 3. So again, I would ask myself, what is my base? I always want to start with my base. So in this case, my base is b. That's the little number over here. E, that's the little number over here. And I know this is going to be equal to something. So now I want to find my exponent. So I tell myself the log is always equal to the exponent. So this log is equal to 3. So that makes 3 my exponent. And then I have my 27. Okay. And we're not trying to solve for anything right now. We're just trying to go from one form, from log to exponential, or from exponential to logarithm. And so on your assignments, you'll have some problems where you have to do that. Okay, so let's go on. Let's try this one. So here we have the square root of 81 is equal to 9. So when in this chapter, when you see a square root, you want to think of it as a power instead of just a square root. Okay, so we can rewrite the square root of 81 as 81 to the half power. Okay, so that looks kind of funny there because of the, so 81 can be written as 81 to the half power is equal to 9. Okay, so if I want to change this to a logarithm form, then we can continue. So my log is going to be my base, which is 81, and then the log is equal to the exponent. So my exponent is a half, so that goes on the right side, and then I have 91. Okay, any questions on that one? All right, so now we're going to look at some properties that are going to help us to solve some of these logarithmic equations. If here we have log a of 1 is equal to 0, and the reason is if you take this log and change it to exponential form, you have a is your base. The log is equal to the exponent, so the exponent is 0, is equal to 1. So anything to the 0 power is going to be 1. On this situation, if you have a log base a and then you have the number a, which are the same, that's always going to be equal to 1. So, and the reason is if we change this to exponential, we get a to the first power is equal to a, and then so on. The last property is going to be used quite a bit, and this is just saying if that's the one-to-one property. If you have two logs and they have the same base, then we can set x is equal to y, and then we're going to be able to solve for the variable. Okay, so let's look at this property. So there's actually two ways that you can solve this property. So we want to know what log 3 of 1 over 27 is equal to. So there's some calculators out there, like the Casio. You can actually type it into your calculator like this. But if you have like a TI 83 or 84 or probably all of the TIs, you cannot type it into your calculator. And so we need other ways to solve it. But don't worry, in section 3.3, we'll use another property that you can just put into your calculator. So for now, we're going to use these other properties. So we want to know what that's equal to. So I'm going to solve it for you in two ways. The first way is to convert to exponential form. So here's my base is 3. So I'm going to write my base. And then the log is equal to the question mark because we don't know what that is. So I'm going to write that as my exponent is equal to 1 over 27. In order to solve that, I'm going to rewrite 1 over 27 with a base 3. So that's going to be 3 to the negative 3. Now the bases are the same. So that tells me that the question mark is equal to negative 3. Okay. So this whole log 3 of 1 over 27 is equal to negative 3. So by converting to exponential form, we were able to solve the problem. So now let's look at these properties. Okay, so if I rewrite this, instead of 1 over 27, I rewrite it as 1 divided by 3 cubed. And I can use the exponent rules and rewrite this as 3 to the negative 3. Then which property does this resemble to our problem? So which of these properties will look like this one? So notice that the base is 3 and then we have a 3. So we come here, we have a base of a, and then we have a base of a. So it's going to look like this property. So according to this property, if a and a are the same here, then the answer should be that exponent. And so we notice here we have our 3 and a 3. So the exponent is negative 3. So that should be our answer. And so that's going to be the case. Okay. So these properties can help you solve these a little bit quicker. But there's a lot of properties. So if you don't want to memorize all these properties, then converting to exponential form can always get you to your answer as well. Okay, so let's look at another one. So here I have pi, and then I have pi, so those are the same. So according to my properties, this answer should equal to what? And so it's going to equal the exponent, in this case 5. So that's correct. So that would be a 5. Okay, let's go again. Now, if you have a log of any base of 1, then that looks like this property. And that's always going to be 0. So our answer here would be 0. So if you remember that any log of whatever base of 1, that's always a 0, then it would save you a little bit of time instead of converting it to exponential form. Okay, so now we can try this one. We have 90 of 90. So that's going to look like this one here. So my answer is just the exponent of 1. So we get 1. And then we have 3 log 3, 8. So that property is this one. Let me see, where is it? Okay, this one right here. So we have the same exponential raised to a log with the same base. So my answer should be x. So in this case, my answer is going to be 8. Okay. So now let's look at another example. So if I wanted to write this as exponential, my base is b, and then I have a 3 as my exponent is equal to 1,000. If I wanted to solve this, then we can see that b is going to be equal to 10. Okay. So in order, you can take the cube root on both sides, or if we see this, in order for this to be equal, the b would have to be a 10. Right, so let's look at this example. Right, so let's look at this example. We're trying to solve for x, but x is kind of trapped in here, so let's see what happens. So if I change to exponential form, my base is 6, and then the log is equal to the exponent, so that makes 5 my exponent. So now I'm able to solve for x. So x is 7,776. And so by changing from one form to the other, it allows us to solve for x. Okay. Let me see. Okay, let's go on to the next one. So in the next sections, we're going to be looking at properties 5 and 6. Those are for section 3.3, which we'll look at or the following week. So 5, 6, and 7 will be for later. But I want to focus on number 8. Somebody said something? Okay. So let's look at number 8 here. So the one-to-one property again, if log b of m is equal to log b of n, then if the bases are the same, we can set m is equal to n. So I'm going to give you like maybe 30 seconds to see if you can apply that property here. Oh yeah, so let me go ahead and put it here. Okay. And so Mr. Mata says that it's going to be 8. So can we use the one-to-one property? And so in order to use the one-to-one property, they have to have the same base, which this one has a base 5, this one has a base 5. Therefore, we can set the parentheses equal to each other. So we get x plus 1 is equal to 9. Subtract 1. So we get 8. Okay. So when dealing with logarithms, whatever answer you get, you do have to check that it is a solution, because remember, the domain is from 0 to infinity. So what you want to do is, once you get your answer, plug it back in for x. So I plug that in here. So I get 8 plus 1 is equal to 9. Whatever you get in the parentheses here always has to be greater than 0. And so 9 is greater than 0. So we're safe. That means that x equals 8 is a solution. Okay, go ahead and try this one. I'm going to go turn my kid's phone a little bit because it's kind of loud. So go ahead and try it. I'll be back in 30 seconds. Okay, so now we have, so Mr. Mata says 3. So let's see if we get 3. The important thing here is to ask yourself, can you use the one-to-one property? Okay, so what is my base on the left side? Do you see a little number like 5 on this side? Well, I don't see a number, so that means that the base is 10, right? And then on the right side, I don't see a number either, so that means that the base is 10. So they do have the same base. So that means I can set the parentheses equal to each other. So I get 17 is equal to x squared plus 8. It's quadratic, so I'm going to subtract 17 on both sides so that everything is on the same side. And now I can, and I drop my, okay, so then let's go simplify. So 8 minus 17 is negative 9. I can add 9 on both sides, take the square root. And so we get x is equal to plus or minus 3. We want to check our solutions. Okay, So if you plug in 3, we get 3 squared is 9 plus 8 is 17. So that's okay. And if we plug in negative 3 and we square it, we're still going to get 17. That's okay. So both of these are going to be solutions. When it's not okay is if you end up with something like this. And I don't remember if I have an example. So let's say you plug in the number. And if you get a negative in here, let's say like negative 4, then that would not be a solution because this cannot be negative. Okay. But ours are producing a positive number in the parentheses, so we're okay. So these are two solutions. So both are solutions. Okay, let's try another one. What is my base here? So I have ln and ln. So remember that your base, this is a natural log, right? So remember that ln is just the same as log of base e. So they both have a base e. So that means we can use the one-to-one property. And so since they have the same base, this has a base e and this has base e, we can set our parentheses equal to each other. So we get x squared minus 3x equals 18. This is quadratic, so I'm going to subtract 18. And so I get x squared minus 3x minus 18. You can either try to factor or use quadratic formula. So this is factorable. And so my solutions are going to be x equals, or my possible solutions, right, are x equals 6 and x equals negative 3. And so we need to check our solutions. So let's check our solutions. Didn't check it. Let me go back. So, okay, so if we plug in 6 in here, we would get 6 squared, which is 36, minus 6 times 3, which is 18, so that would work. And if we plug in negative 3, we would get negative 3 squared is 9, minus negative 3. Let me write it out so we can see it. Okay, so we have natural log of negative 3 squared minus 3 times negative 3. So we would end up with natural log of 9, and then negative 3 and negative 3 is positive 9. So it gives us 18. So that's okay. So both are solutions. Okay. All right, so let's try this one. And let me go back. Okay, so here I have log 4 of x plus 6 plus log 4 of x minus 6 is equal to 3. So this problem is a little different because it doesn't look like this where I have one natural log on one side and another on the other. Now it has two natural logs on the left side and a number on the right side. Okay, so in the next section, 3.3, we're going to learn the properties, which are 5, 6, and 7. So we'll be able to apply one of these properties, property number 5, to this problem so that we can solve for our question. Okay, so it looks like I left this for something for you to look forward to, right? But yeah, so in the next session that we have, we'll look at these properties. So we'll be able to combine the two logs on the left side. We'll be able to combine it as one log. Okay. And so I think we have like a few minutes left. So what I want to do is share my screen so I can show you the calculator really quick. Let's see. Let me share my entire screen. I happen to have a calculator so I can show you what it looks like. Let me just open it up. Let me just open it up. Wait, Mama. Okay, hold on. All right, so let's see. I think Let me open this one. Okay, yeah. So can you guys see my screen? Let me make sure that you can see my screen. Okay. So if you can't see my PowerPoint, let me know. But let me just scroll down. I want to show you. Next week we'll look at this PowerPoint, but I wanted to show you the calculator. So here, and I heard a. Let me make sure that. Yes. Okay. Cool. So if you have a TI-83, you can see the log key is right here, and then the natural log is right here. So when you're working with the number e, it's gonna be where the natural log key is. You can see the little e, and then in order to reach that, you have to go second e. On the Casio calculator on the right, um, the log key is here, and notice it has boxes, so you can actually put in the base and then the number and the natural log. If you have an 83 or 84, it's okay. You don't have to go by a Casio, because in this next section, you'll actually be able, I'm going to show you how to basically do these problems, like this problem, in your calculator as well. Okay. So next week, I encourage you, if you join us, if you have your calculator, go ahead and have it out so that you can also follow along and enter it into your calculator. Okay, but that was some examples from 3.1 and 3.2. And so we have about 10 minutes. So if you have a question, you're feel free to stay here, ask your question. And if not, then we'll see you. I'm going to pass it over so they can tell us when our next session will be.
Thank you, Ms. Chuka. If you can just let me know if you can hear me real quick.
We can hear you.
Awesome. Thank you so much. So thank you again for your presentation. If anyone would like to download the copy of the presentation, you can go to the top right corner and click on the little box going down. We do want to remind you all about the previously recorded sessions, which are available on the YouTube playlist. This session will also be available on that playlist later today. Before you all leave, I want to share the TV sessions that we will have next. At 3 p.m. today, we will have a presentation on EPCC music with Yasmin Flores. And join us again on April 14th, the week after next week after Cesar Chavez Day, at 11 a.m. for Happy Math Hour, where Math 1314 will be covering linear and nonlinear systems, and Math 1324 will be covering the review for exam 3. The 1 p.m. session for that day is the reading workshop with Rose Galindo. Thank you all for coming in today. We hope you all have a lovely weekend. And if you have any questions, feel free to use the chat box or your mic. And we hope to see everyone again for Happy Math Hour. Thank you.